Hi everyone, my name's Mike Cook. I'm an AI researcher and game developer currently based at Queen Mary, University of London, and this is the Getting Started in Automated Game Design tutorial. Over the next 90 minutes, I'm going to take you through the past, present, and future of automated game design research with the aim of getting you motivated and excited about this cool new research area, and hopefully giving you some tools that will let you get started on your own systems. As we'll see over the course of the next hour or so, automated game design is as much about art as it is science, and each person brings their own perspective to the work. So before we dive into the tutorial itself, I wanted to give you some background on what my perspective is. I hope you enjoy everything I have to say in this talk, but I also hope it leads you to find your own perspective on AI and game design. So make sure you take everything I say with a pinch of salt, and I look forward to playing and learning about your games and systems in the future. I started my PhD almost exactly 10 years ago now, in October 2010, and in 2011 I began creating a very simple AI system that combined level designs, rule sets, and piece layouts to design simple arcade games, which I called Angelina. I kept this project name as I developed new iterations of the software, experimenting with things like designing mini Metroidvanias inspired by news headlines, entering game jams with weird three-dimensional nightmare worlds, and editing code to invent game mechanics for puzzle platformers. My research has been greatly influenced by computational creativity, which is a subfield of AI that's interested in how AI can do things that we normally describe as creative when a human does them. So things like composing music, painting, designing video games. As a result, Angelina has developed into a system not just concerned with designing games, but with being perceived as a game designer by other people. The latest version of Angelina can stream its design process on Twitch, write descriptions of its games, and interact with its audience to gather knowledge, ideas, and feedback. And we'll be touching on some of these ideas later in the tutorial. At the same time, I've continued to practice and develop as a game designer myself. As a designer, I'm most interested in using procedural generation to enable new kinds of game experience, but I've also found myself increasingly interested in games that allow the player to modify or recombine rule sets to create new rules or capabilities, something which I think is directly inspired by having worked with AI game designers in my research. You can hear a little bit more about my game design work in a paper I'm presenting at COG this year, Procedural Generation and Information Games, which I've linked to in the description of this video. So in this tutorial today, I'm going to take you on a tour of automated game design and try to give you some of the lessons that I've learned, the everyday techniques that I use, and my perspective on where this field is going. My aim is to guide you past some of the mistakes and pitfalls that I've made, and to give you the motivation and confidence to know how to get started, and also to offer some guidance on promising ways to begin research in this area. So to make this tutorial a little easier to digest, I've broken it down into a few parts, and I've left timestamps in the video description to help you jump around in case you want to take it piece by piece. The only thing I would say is that you probably should watch the parts in order. So in the first part, we're going to look at what automated game design is and look at the history of the field and what we can learn from that. Then we're going to talk about why we would want to automate game design, what kind of impact it might have on the games industry and society at large. Then we're going to look at some practical issues in building one of these systems, and I'm also going to introduce you to BlueCap, which is an open source automated game designer example that I built specifically for this tutorial. And finally, I'm going to talk to you about some future issues about creativity, about communities, and then the kinds of problems that you might want to tackle when you build your first AGD system. I'm always super excited to talk to people about any of these topics, so if you ever do want to chat with me about procedural generation, automated game design research, making games, playing games, and anything in between, you can always get in touch with me on Twitter @mtrc, or drop me an email, mike@possibilityspace.org. Let's get started. So let's begin by asking, what does automated game design actually mean? Now, throughout this talk, I'm going to use that term, or sometimes its shortened form AGD, to describe a particular set of research areas and systems. But in reality, there is no official definition for what automated game design means, and there's no clear boundaries that divide what research is in and out of this group. In actual fact, if someone else was giving this talk, they would probably draw different distinctions than the ones I'm going to over the following few minutes. One of the reasons why this is so tricky to define is that the research is concerned with things which are also very hard to define. So the notion of being a game designer has a specific meaning in the games industry, but when we talk about automated game design research, we're referring to more than just the tasks a game designer takes on. Really, we're describing anything to do with the development of games, but I like the term automated game development less because it emphasizes technical aspects more, and the field already has a significant bias away from artistic and design problems. Beyond the term game design, we have even more complicated issues, like the ongoing discussion on what exactly constitutes a game. And these are conversations that scientists are quite bad at having, but it's worth noting that actually a lot of people in the games industry struggle to be open-minded in many of these instances too. That might make this field sound intimidating, but I love working in this space precisely because its definitions are so fluid, and because so many different groups are responsible for shaping them on a daily basis. It also makes it easier to strike out in a direction that you think is promising and just start working. There are a lot of unanswered questions in this field, as we're going to see in this talk, and there really isn't much to stop you from just getting stuck in. Today, we're not going to worry about hard definitions. Instead, we're going to take a quick look back at the history of automated game design research and use that as a guide to get a feel for what this research area is about. And as we'll see, over the last decade or so, there's been a huge divergence in different approaches, and today automated game design research comes in many shapes and sizes. So we're going to start in 1992. The first system that I usually put when I'm telling the story of automated game design's history is Pell's METAGAME system. METAGAME designed what Pell called symmetric chess-like games, which you can think of as games that you could design if you were given a chessboard and all of the pieces that go with it. Even though it's one of the earlier examples of an AGD system, its approach has a lot in common with modern AGD systems. It has a bespoke design language to describe its games, much like the one we'll be defining later, and it uses simple static analysis to look for problems with games and filter them out. Another example, which comes 15 years after METAGAME, is Browne and Maire's Ludi system, which designed abstract strategy board games. One of the major contributions by Ludi was the extensive list of expert-designed metrics for evaluating the games designed by the system, which studied many different factors in what Browne and Maire considered to be a good strategy game. These early systems had only one focus, generating rule sets for games, and they targeted games where rule sets were really the entirety of the game design. And we can think of this as a natural extension of the role of games in the history of AI, which generally concerned itself with abstract physical games like chess and Go. And this is partly because these games posed hard search problems, but also because these kind of ancient traditional games were seen as intellectual pursuits, and thus were respected in a lot of highbrow scientific spaces, which is still something that continues to this day. Between 2000 and 2010, however, there was a large growth both in the number of games-focused study programs at universities and a growth in the number of people doing dedicated game AI research. CIG, the precursor to this conference, began as a symposium in 2005 and became a full conference in 2010. AID, another major games conference, began in 2005, while the Foundation of Digital Games conference ran for the first time in 2009. At the same time, games themselves were changing drastically too. Independent game developers were now getting a lot more attention in the press, and the online distribution of games, combined with console-led indie publishing programs, were allowing different kinds of games to be made in different ways to before. During this time, the idea of proceduralism became very popular among certain circles of developers, critics, and academics. Proceduralism is the idea that when we build models and systems of things, especially for video games, we convey messages through how we build these systems and how the player experiences them. Proceduralism was extremely popular during this period. Jason Rohrer's Passage came out in 2007, along with Rod Humble's The Marriage, and in 2008, Jonathan Blow's Braid came out. All three of these games were regularly cited as examples of procedural rhetoric, along with news games which were growing in popularity at the time. The internet was awash with essays and blog posts about what these games meant and why this was the future of meaning in games. Michael Mateas, who now runs the Expressive Intelligence Studio at UC Santa Cruz, wrote in 2008, "Code is a new kind of writing. New media scholars must read code at the level of procedural rhetoric, aesthetics, and poetics encoded in a work." This marked the beginning of a period where a flurry of important AGD systems emerged from work at UC Santa Cruz. The first is this Untitled project led by Mark Nelson, which constructed simple mini-games based on plain English prompts like shoot pheasant. And as far as I'm aware, this is the first automated game designer that has a visual component. It can select art from a database to illustrate its games based on the prompts. It can also design games from different perspectives, so the prompt shoot pheasant might result in a game where you play a pheasant avoiding bullets, or a game where you fire bullets at pheasants who are flying around. And a couple of years after this project, the Game-o-Matic was released, led by Treanor. This was one of the first examples of an assistive automated game designer, originally conceived as a tool for journalists to make news games with. The Game-o-Matic had a library of micro-rhetorics, which were like fragments of game designs that had particular interpretations attached to them. So for example, if an object A gets smaller when an object B touches it, the player could interpret this as B eating A. The Game-o-Matic was able to select, combine, and tweak these micro-rhetorics from a big catalogue to make full game designs, and it would tailor them to match whatever concepts and relationships it had been given to work with. I started work on my own AGD system, Angelina, around 2010, but in 2012 I began to move away from abstract arcade games and think more about representing other parts of the game design process. Now, at the time I was mostly unaware of what was happening in Santa Cruz, but I was really influenced by research in computational creativity. My PhD advisor, Simon Colton, advocated for handing over responsibility to AI systems in order to help them become more independent. And this led to the development of a new version of Angelina, where I gave the system the ability to design not just the rules and level design, but the selection of music, sound effects, and artwork. Although it didn't have the sophistication of the proceduralist approaches emerging from Santa Cruz, it was another way in which AGD systems were beginning to incorporate different parts of the game design process. The push for proceduralism forced AGD systems to consider how games communicate ideas, which naturally led to the consideration of factors outside of just rule sets, like the selection of appropriate visual content. At the same time, other systems like Angelina were trying to take on more responsibility in the creative process, which also transitioned them away from a pure focus on rules. AGD systems were expanding to tackle multiple creative tasks at once. In 2014, Antonios Leapis, Yorgos Yannakakis, and Julian Tegelius published a paper titled Computational Game Creativity, in which they described automated game design as a process of orchestrating different types of content generation. So in other words, solving not just a procedural generation problem, but solving a procedural generation problem while making sure you are working together with the rest of the game's design. And we can clearly see this reflected in many of the AGD systems in this era, as well as dozens of other similar design systems that were made during a similar period. Today there are more automated game design systems than ever before, working in many different genres and modeling different kinds of game design activity. This is footage of Germinate, the latest AGD tool to emerge from the work at UC Santa Cruz, and the work of many different researchers, including Adam Somerville, Max Kreminsky, Sarah Harmon, Joe Osborne, Chris Martins, Noah Wardrop-Fruin, Michael Mateas, and many more besides. Germinate is built on top of Gemini, a rich and complex AGD system that can design games based on descriptions of their intended meanings, but it can also do the inverse, extracting possible meanings from existing game designs. We can see some of the ideas from the Game-o-Matic being extended and expanded upon here, as well as a lot of innovative work being done on co-creative interactions, as demonstrated in this video. We've also seen some impressive systems that actually result in fully functional, playable standalone games. So Data Agent, which was developed by Gabriel Barros at NYU with Michael Green, Antonios Leapis, and Julian Tegelius, is a murder mystery system that generates quite complex puzzle games using real-world data. The Data Agent team wrote an excellent paper advocating for maximalist game design, and the project is one of the most accomplished examples of a playable research game in existence, I think. Matthew Guzdial's work on applying machine learning to automated game design is another example of exciting new paradigms opening up brand new approaches to the field. This system learns the structure of games by watching gameplay recordings, and then builds up an internal model of how it thinks the game works. Once this has been done, multiple learned models can be blended between to create new designs that combine or interpolate different aspects of other games. I really recommend looking this work up, as well as Matthew's related work on co-creative design tools, especially if you're keen on applying machine learning to AGD yourself. In a similar vein, the work of Ahmed Khalifa and others at NYU applying reinforcement learning to level generation is also worth a look. RL is applied to generate levels for multiple games from the VGDL corpus, including Zelda and Sokoban, which means it gets a chance to explore how changes in genre or subgenre affect the nature of the learning task. Also at NYU is the Baba Is Yall project by Megan Charity and others, which is a mixed initiative system which you can play online right now, testing Baba Is You inspired levels, designing your own, and even watching AI try to solve them. This is a particularly notable example because Baba Is You is in some ways a game about game design and general game playing, and so getting AI to play and design for this game is an especially intriguing and meta-level task. And finally, one example that I couldn't leave out is Super Mash, a commercially published independent game developed by Digital Continue and available on Nintendo Switch and PC. Supermash lets the player mix up two game genres like JRPG and platformer, and then generates short, blended game experiences that mix up the genres in unusual ways. The generation process is very constructive, but has some real systemic flair, as well as looking absolutely gorgeous. Supermash is a weird, wild, and sometimes broken game, but it's also one of the bravest and most technically experimental games I've seen in a long while, and I think it absolutely deserves a mention here as evidence of how AI-based game design is slowly creeping into the games we play every day. Before we close out this history lesson, I wanted to add a little footnote. So in 2015, Gillian Smith and I wrote a paper where we argued that automated game design was too focused on rules and game mechanics as the center of all of its systems, and that if we didn't do something to change this, we risked rules becoming the center and most important thing about automated game design research. We suggested that focusing on genres of game where rules were underemphasized or even non-existent, like walking simulators, would help us develop the field and broaden its scope. As you can see from this potted history of the field, in the 5 years since we published that paper, not a lot has changed, and most AGD systems still do focus on rules. And I say that as someone who has built half a dozen of these things, all of which did exactly that. Building AGD systems that deal with different problems, like art direction or soundscape design, is extremely difficult, and I've abandoned more than one project in that area. Now, the takeaway here isn't that these systems are impossible to build, nor is it that it's bad to make AGD systems about game mechanics or rules. It's simply a reminder that games are bigger than this field, and they're definitely bigger than any one AGD system. Game design is a creative practice that is expanding and changing all the time, and that quality of being a moving target is one of the most exciting things about it. As long as we keep trying to expand our thinking and look beyond what we're currently doing, we can keep automated game design research alive and vibrant. No two games are alike, just like no two game designers are alike. And for the same reason, we shouldn't expect any two AGD systems or AI researchers to be alike either. Everyone comes with their own perspective to this field and their own problems that they want to investigate. And that's why we don't need to worry about every system covering every aspect of game design. I really like this quote from V. Bucknam's Manifesto for Making Games. It encapsulates a particular kind of openness and optimism that I find really appealing. And that's also what I want you to take away from this history of the field. There's no convergence on a correct way of doing things. The process of building an automated game designer is as organic and personal as the process of building a video game. And every new AGD system always brings us new insights and inspiration for that very reason. For me, this is one of the best things about working in this area. This brings us to a new question, which is why? We've seen how, over the history of automated game design research, we've moved from a fairly narrow field focused on the abstract to a bustling place with many researchers pursuing different design philosophies. But to what end is all of this research being done? Why exactly are we building all of these complex and often bemusing systems? I often leave this reason for last when making lists of researchers' motivations, but I think it bears listing up front here. A lot of people become researchers because they love a challenge. There's something deeply appealing about wondering if something is possible and how we might be able to make it happen. That's a great reason to do something like this, because we learn so much along the way that even if we never reach the summit, the new discoveries make the trek worthwhile. Another reason that's often raised is the ongoing and escalating crisis of labor in the games industry, specifically in the medium to large commercial games companies that make some of the biggest and best known games in the world. The games industry exploits its workers in many different ways, but one of the best known and most destructive of these is the extent to which game developers are overworked to the point of exhaustion, and how normalized this has become for both developers and their audiences. This is sometimes known as crunch. For a contemporary example of this, CD Projekt Red have admitted to working under crunch since January of this year to finish their latest game, Cyberpunk 2077. This long period of crunch that exceeds even the already high levels in the industry is colloquially referred to as a death march. Often we propose that automated game design systems might help alleviate some of these problems by providing tools that reduce the workload for teams, allowing them to make the games that they want within normal working hours, and perhaps even automating away tasks that are considered repetitive or less enjoyable. However, it's absolutely the case that some of the games industry's problems with crunch, mismanagement, and other issues could be alleviated with certain AI systems. Despite this, we very often write papers about procedural generators and automated game designers where we explain that this system will reduce the workload on developers in large game studios. This, I think, gives the games industry a little too much credit. If we straightforwardly make games easier to make, games will either get bigger or companies will lay off workers until crunch is necessary again. So when we say there's a crunch crisis in the games industry, I don't really see AI as a simple solution to this. But I do think AI can potentially be part of a solution. Instead of thinking about how AGD systems can accelerate the manufacturing of a product, instead we should think about their ability to empower individuals. And the best way to do this is not to study their impact at the largest and most resource-rich companies, but to look at the needs of creators across the medium of games. Instead of asking how we can support successful large businesses, who are successful at least in part because of their broken and exploitative business practices, instead we should ask ourselves, why are smaller developers not able to find a sustainable income for their work? And why do they struggle to create the kinds of games that they want to? Can we build systems that help make this easier? The answer won't always be yes, but I think that this is a better starting point for doing AI that serves the public good. Beyond this, I think automated game design and computational creativity in general has a big role to play in advancing how people are creative on a day-to-day basis, and how creative work is integrated into society. Creative communities provide support, mentoring, growth, feedback, inspiration, and camaraderie to the people who create within them. And you don't need to be a professional artist leading a movement to benefit from one. We're in creative communities with our friends, our co-workers, and our family. But maintaining creative communities and making sure everyone is served by them takes time, work, and other resources, which not everyone has equal access to. Automated game design systems could become important parts of these communities, helping support and maintain these groups and helping everyone grow and be creative on a casual basis. I'll talk a little bit more about how I see this being possible at the end of the tutorial. There are many more reasons to do this research than the few that I've been able to list here, but helping people create more freely, more confidently, and more happily are all great reasons in my opinion. So the next question is, how exactly do we get there? It's tempting to think of scientific progress as a linear path that we slowly move along until we get to a big goal at the end of it. We often frame research problems in these terms, for example, building AI that get better and better at playing a particular video game until they beat a human expert, like OpenAI's adventures in beating the world champions at Dota 2. This simplified way of thinking about progress is easy to communicate, which makes it appealing to both press and the public, and easy to evaluate, which makes it easier to write papers and argue that the field is moving forwards. We're led to think of technological progress along two axes: the amount of resources put into a system, whether that's time, computation, or something else, and the impact of the output, which again might be in terms of perceived quality, commercial worth, cultural value, or something else. Typically, efforts are made towards reducing the computational resources involved and increasing the impact of the output. So if you can make a spaceship that goes to the moon and costs $10 million, then making it cost $1 million, that's less resources, and go to Mars, that's more impact, is just seen as straightforwardly good. For automated game design, as with many creative domains like art and music, this thinking leads us to focus on what I call the infinite Rembrandts problem, where we imagine the ultimate goal as a system which produces high-quality creative work with very little time or computation. During the early years of my work on Angelina, the most common question I would get in interviews with press is how long does it take Angelina to design a new game? The follow-up would often be, could I imagine a world in which someone could press a button and receive a brand new AAA video game just a few minutes later? This is a captivating science fiction idea, but it's not a future that I see as particularly interesting or even likely. There are many reasons why this doesn't fit into the way that we enjoy culture as human beings. In talking about a similar problem, the computational creativity researcher Simon Colton poses that we enjoy creativity not just because of the things that are made, but because of the processes, backgrounds, and motivations of the people who make them. As he puts it, creativity in society serves various purposes, only one of which is to bring into being artifacts of value. But you don't need to get deep into philosophy to see why such a creative system isn't very appealing. For one thing, for most of us there already exist more AAA video games than we could ever hope to finish in our lifetime. In a sense, we already have a system for pressing a button and receiving a new AAA game. It's the New Releases tab in the PlayStation Store. One reason why I think this idea resonates so strongly with us is that it aligns with the view of games as a commodity in a business first and a creative endeavor second. Because the games industry is so often framed in economic terms, from the specs of a new console generation to the budget and earnings of its biggest studios, our ideas about what the future could mean for games are inevitably shaped along these lines too. Games, and video games especially, have a huge identity problem, and as a medium they suffer from a lot of insecurity. After struggling for acceptance for so many decades, the way that acceptance has manifested is largely a result of being important financially. And if you've ever written a grant application about games research, the chances are you've quoted some figure about the size of the market or how fast it's growing. Instead of thinking about how automated game design can fit into the ways we already make games, it's better to think about automated game design as a new tool. A tool that can be used by researchers, but also by artists, by designers, by teachers, by everyone interested in making games. They change who can make games, how we make them, and the kinds of games that it's possible to make. So with that in mind, let me propose 3 different applications for automated game design that are a little bit different from the infinite Rembrandt zone. First, let's look at this corner of the highly scientific graph we just made. Down here in the left, we're looking at systems which don't need much time or a big computer to run on, but unlike the infinite Rembrandt zone, they don't need to produce games of great complexity or depth. And my example for this is what I call coffee break games. So imagine you're sitting on a bus, waiting for an appointment, or just putting off going to sleep for 5 more minutes. You pull out your Nintendo Switch, tap on the 2-minute minigames app, and Angelina generates a short and sweet puzzle game about counting sheep. You play the game, complete it, put your Switch away, and never ever look at that game again. So what things are we looking for in an AGD system like this? Well, one priority is that the design time needs to be very short. In fact, the ideal model for this would be equivalent to generating a level in a game like Spelunky, so short that the player doesn't even notice it happening. And that could be a real challenge, because most AGD systems need at least a little bit of time to test a game to see if they're playable. In terms of output quality, there's a real need for the system's output to be polished and bug-free. So the game doesn't have to be a masterpiece, we'll get to that in a second, but because the system serves its output directly to the player, there's absolutely no chance for a do-over or a round of feedback or anything else. The priority has to be on producing games that work. Fortunately, we don't require the games to be novel at all. In fact, novelty isn't just unnecessary here, it's actually a bad thing. If the games generated are too novel, the player won't be able to learn them and start playing within a few seconds. So an AGD system working on coffee break games would probably be best off remixing common ideas to find entertaining variations that were still instantly accessible. Let's go back to our very scientific graph. So moving along the resources axis and just a little further up the impact axis, we reach a spot where AGD systems are given a little bit more time and computation to work with, and an opportunity to make games with a bit more impact than our 5-minute coffee break distractions. And here we can find a type of AGD system that I'm going to talk a lot about later that I call community scale AGD, or if you prefer, game design buddies. These are AGD systems that can make reasonable sized games on their own, as well as play and analyze games made by other people, offering help and feedback. And we might think that by increasing the resource cost, we're making a system that's less accessible, that has to run on big expensive servers somewhere. But instead, these systems solve the resource problem by just making games more slowly. And the result is an AI system that works on timescales that people can actually relate to. What this means is that these systems are always running, sort of like a desktop pet that you might have had in the 1990s. These systems are always working on something, and you can check in at any time to see what it is, offer feedback, maybe design part of the game yourself, and have a dialogue with the system about what it's doing. Imagine something like this on a computer in a classroom, or running on an old laptop at the back of an indie studio, or maybe just sitting at home on your desktop. These little game designing machines will learn from you, which changes the kinds of things they design, and together you explore a world of game design together. In terms of our wish list for a system like this, first off we're looking at a design time measured in maybe weeks or months rather than minutes. These systems emphasize the process of making games, not the finished product, and so we only need to release games when they're finished. We're not in any rush. When you think about it, this makes a lot of sense in social contexts. Most people make games at a rate slower than this, and that's where a lot of interesting creative interaction comes from. You have the excitement of watching a game develop, waiting for its release, maybe giving feedback on an early build that someone sends you, and then sharing the finished product with others and reflecting on the process. In terms of quality, we don't necessarily need the games to be flawlessly high quality. Much like the games that you and I might make, they might have some rough edges on them or not have every idea executed perfectly. The important thing is the act of creating it, what lessons the AI can learn from each finished game, and how that leads it to make better games in the future. And all of this gives its audience an opportunity to get involved too. And there's a similar story with novelty too. The novelty of a system like this can be purely local to the community the system exists in, rather than aiming to be completely novel across the entire history of games. We'd hope that the system could surprise the people around it, but it needn't be revolutionizing the entire field of game design. We'll talk a little bit more about this idea of community scale AGD later in the tutorial. Finally, let's stretch up into the far top right of this graph where the resource cost is high and so is the impact. The greatest irony about the infinite Rembrandt zone as a decadent luxury AI system is that it actually isn't that ambitious. So for the third and final example in this section, I want to look at an AGD system that aims to change games fundamentally forever. And I call this century scale AGD. So the premise behind a system like this is that it aims to create a single piece of work, but that work is of such immense impact that we would be willing to wait for any length of time and spend any amount of computation to receive it. An AGD system that exists at this spot in our graph is designed to work for decades, if not centuries, on a single game, and this is by design. We might think, well, if it takes 100 years to make a game, why not just double the computational resources we give it and get a game in 50 years? But what I'm proposing is that even if we could double the resources in this case, we would simply want to let it run for twice as long again, so as to increase its impact even further. The length and depth of the system's design process is part of what the system is. Now, the quality requirement of such a system is astronomically high. The resulting game should be so important and impactful. The people that live to play this game for the first time will have been watching this system work for their entire lives. The people who built and maintained this system have died. The expectation is that not just the game, but the process of designing this game will have a lasting cultural and artistic impact and be remembered for centuries to follow. Similarly, in novelty terms, a game made by such a system wouldn't just be a novel idea, but would fundamentally change the way games were talked about, thought about, made, and played forever. These are just a few possible futures for automated game design, but I think they're all more interesting and more likely to happen than our imagined infinite AAA shooter machine. They're also all very different engineering challenges, demanding a wide variety of different approaches. Automated game design is a toolbox. It's a new way of thinking about modeling, exploring, and enjoying design spaces, and that's what makes it so difficult to imagine what it might let us do. We've talked about what automated game design is, and we've looked at the history of the people and systems that made up the research field so far. And we've also discussed the kinds of things that we might want this research to do in the future for society. Now it's time to talk about the practicalities of actually building one of these systems, from initial sketches through to publishing and distributing the games that it makes. Throughout this section, I'm going to illustrate some of the topics we cover by referring to BlueCap, an open source automated game designer that I built for this tutorial. BlueCap is a very simple, toy-like example of an automated game designer that designs two-player abstract games like Noughts and Crosses or Connect 4. It's written in Unity with C# and comes with some starter scenes for playing and generating games. Hopefully by now I've convinced you that automated game design can and should be much more than just rule set generation, but this simple system is perfect for exhibiting AGD systems using examples that are hopefully familiar to many of you. It's got a little bit of everything in it, so I really hope it'll be a useful starting point for your own experiments. So the first thing to point out is that I won't be using this section to teach you about specific techniques like coevolution or mapper leads. And the main reason for this is that there is no single best way to do automated game design, and we certainly don't have enough time to go over all of the ways people have tried to do it. But more importantly, algorithms are something we already spend a lot of time writing and talking about. Instead, I'd like to focus on aspects of the process that we don't really discuss in papers and talks. I find that a lot of the most important knowledge and lessons learned when doing AI research often goes unwritten. And that makes a lot of new areas harder to get into because these hidden traps and pitfalls are often not pointed out to newcomers. So the first step in building pretty much any generative system is laying out the space that you want to explore. And what we mean by this is defining the range of possible outputs that we're interested in our system trying to produce. We don't have the time, money, or mental energy to try and build a system capable of generating any kind of video game. So we're going to have to pick and choose a smaller area to explore that we find interesting and worthy of study. I like to start out with a rough statement summarizing the area I'm interested in. So for BlueCap, I chose quite a small starting point: two-dimensional, two-player, turn-based strategy games. Now, a few of these choices in particular I'm making ahead of time to simplify my life later on. So turn-based games are a lot easier to evaluate than real-time games, as are two-player games. Two-dimensional games are also a lot easier to make look nice, especially if you're not great at art. So even this statement covers a huge space of possible games. So there's a little exercise that I like to do to narrow down the space a little bit before I get designing. So what we're going to do is define our space by thinking about the results that we'd like our system to come up with. So the first step is to define what we call an inspiring set. I like to think of this as being like marking out the edges of the space that we want to explore. This inspiring set is a list of outputs that we can describe in detail. We could even make them by hand ahead of time. Often they are famous examples in the domain that we're already trying to work in. For example, if we're building a level designer, we might pick a few famous levels from our favorite games or sketch out designs that we would expect our system to be able to generate. For Bluecap, I started with a few simple games that were already in that category that I defined just now. So Noughts and Crosses, which you might know as Tic-Tac-Toe, Connect 4, which I used to play a lot when I was a kid, and Reversey, which you may have seen on Windows as a free game, or maybe you've played it with a physical set yourself. So these are all games that fit into our definition of turn-based, two-player, abstract strategy games. The next step is to review our inspiring set to get a feel for the kind of design space this marks out. So in order to check this, it's useful to imagine trying to transform one member of the inspiring set into another. So we can do this informally, doesn't need any code, we just note down the kind of changes that it would require. So we're looking for two things in particular. How many times do we need to change the game to get from one to another? And what nature are these changes? Like how big and how significant are they? So to transform Noughts and Crosses, or Tic-Tac-Toe, into Connect 4, we need to increase the size of the board from a 3x3 grid to a 7x6 grid. And straight away this tells us that the size of the play area will probably be something that we want our generator to have control over. We also need to change the victory condition. The two games have quite similar victory conditions, but one is 3 in a row, whereas the other is 4 in a row. So this is another variable that we probably will want our system to be able to control, the number of pieces in a row required to win. And finally, we need one more rule to make it Connect 4, which is a rule that applies between player turns. So when a player places a piece on the board, as it were, it should fall down to the bottom. And that's because Connect 4 is played on a grid that's kind of like standing up, so you drop pieces in from the top. But we can simulate that here by just having the pieces fall down after the player has placed them. So each of these small changes will inform the design language that we're going to describe in just a second. But importantly, the number and complexity of the changes tell us a lot about the size of the design space that this inspiring set is kind of defining. So if there are too many changes required, or if the changes are extremely fundamental, this will make it harder, although not impossible, to build a system that encompasses the entire breadth of the inspiring set. And it might mean that subsequent tasks, like evaluating the games, are also harder. We also need to look at how drastic individual transformations are. So for example, if your inspiring set contains level designs, and one is a 3D level and the other is a 2D level, that might be too drastic to bridge between with a single system. In the case of rule sets, for example, I try to make sure all of my inspiring set games share a control scheme, or at the very least that there's kind of a superset of the controls that isn't too large. This tends to make evaluation a lot easier, as we'll see later on. So for Bluecap, the space we've marked out is actually a little on the small side. The games are quite similar to one another, and the changes required are actually also quite simple. And this can mean that the resulting design space is too small, but fortunately there are ways that we can improve this as we build the system. So the next step that I find useful is to establish landmarks in the space that we're slowly marking out. A landmark is something which we can express by mixing together bits of our inspiring set, possibly with a few modifications. So landmarks can be very lazy. They don't need to be innovative or good or really clever games, and they don't need to be tested. You don't need to make sure that these are good games. They just need to be relatively well-formed examples of games that would be in your design space. So I like to look for kind of midpoints between two examples in the inspiring set. And although that I've used a triangle here, that's just because my inspiring set has 3 games in. Yours might have 4, or it might have 8. It might just have 2. But you just need to pick like a few to blend between and see what those landmarks look like. So this is a good way to test out the density and texture of your design space. So is it hard to think up a plausible example, or are there actually loads of good ideas occurring to you as you mix up these components? This will give us an idea of whether this space will be easy to search or not. So you can see for Bluecap, I've come up with things like Super Tic-Tac-Toe, which is noughts and crosses, but on a Connect 4 sized board. So we kind of already alluded to that before. So it's kind of like Connect 4 without gravity. Or Battle Tic-Tac-Toe. So this is, you're aiming to get 3 in a row, but you can flip pieces like in Reversey. This game is actually broken, if you actually think about it, but it's game-shaped. It makes sense as a blend. It wasn't too hard to come up with, and that's fine. That's all a landmark has to be. And the third example there is Graversey, which is Reversey, but it has Connect 4's rule that makes pieces fall down. So these 3 games, they're very simple. They're really just mixing together rules from different parts of our inspiring set. But they were very easy to come up with, which probably means that there are more designs in that space that are similarly easy to discover, and it's not too hard to kind of apply one rule from one game into another game. So these are all good signs for BlueCap. So once we have these inspiring games and the landmarks laid out, we can begin to think about what our design language will start to look like. At this point, I want to interject to say that I actually have a paper at COG this year about the drawbacks of design languages and a suggestion for an alternative way of working. But despite this, I still use design languages all the time. I think that they're easy to use, they're fast, they're fun, and they get pretty good results. So if you've already seen that paper, don't get confused by my use of design languages here. I'm still super in favor of them. But if you're curious about what other ways of working might be possible, I would encourage you to check out that talk. I'll put a link in the video description. So we've defined our inspiring set, we've defined a few landmarks, and now it's time to precisely define what language we want to use to build games, levels, characters, or whatever else we're dealing with. Now, the exact nature of the design language you need will greatly depend on the kinds of algorithms and techniques you plan on using, but there's still some general things that we want to watch out for. Whatever our design language is for, whether it's designing levels, composing music, or writing game rules, there are a few common considerations and challenges. We want a design space that contains a lot of surprising, novel, and high-quality outputs, which means a bigger and more complex design language is always going to be better because it lets us express a wider variety of designs. But we also need a design space that isn't too big, and one where the ratio of good to bad outputs is not too small. The bigger our design space, and the smaller the ratio of good to bad outputs, the harder it will be to search, and the more computational resources we'll need to dedicate to it. This means that every small decision about our design space is important. For example, we know we want to have variable size boards because our inspiring set games use different size boards. So how big should we allow the boards to be? A good starting point is to use the limit suggested by our inspiring set. So noughts and crosses is the smallest at 3x3, and reversey is the largest at 8x8. We want to give our AGD system some room to experiment in though, so we might want to extend our limits a little. In this case, we probably don't want anything smaller than a 3x3. The space is a little tight, and even noughts and crosses has problems on its 3x3 board. But we could let boards get a little bit bigger than 8x8, perhaps to 10x10 as the maximum limit. Now, one criticism of this range is that it includes a lot of redundancy. For example, a 5x10 board isn't very different from a 10x5 board if you're playing a game like noughts and crosses. And most games that work on a 9x9 board would probably also work on a 10x10 board. So if we agree that this is unnecessary, we could restrict this access to a set of common board sizes instead of just using arbitrary values. So for example, we could only allow square boards, and we could even restrict it to a set of 3x3, 5x5, or 9x9. This massively reduces the task of choosing a board shape. However, there are drawbacks to this very drastic approach. For example, one of the rules in our design language is that pieces fall down. That's the rule from Connect 4. So in a game with this rule, a 5x10 board is very different from a 10x5 board because of the gravity being applied to player pieces. And similarly, while most games might not play differently on a 9x9 board to a 10x10 board, there might be a particularly genius game that uses patterns of 3, and having a board length that's a multiple of 3 might be crucial to making that game work. So this is obviously a hypothetical claim. We don't know whether this game exists, but we might have a hunch or a hope, and thus want to keep that option open. So this is a classic trade-off familiar to anyone who has made a procedural generator before. The broader you make your design language, the more potential good things you include, but you also make the task of finding the good stuff harder. This is a list of all the components we get from the process of transforming one inspiring set game to another in BlueCap, and it's a good starting point for our game. From this, we can start to think about the next important part of our design, the structure of a valid output and how to generate one at random. So first, what components are necessary? Well, every game must specify the size of the board, so that's necessary. And for BlueCap, we also want every game to have a win condition. Now this one isn't a necessity, so we might want to design games with no end, so there's no win condition needed. We also might want our system to have the freedom to design games where you can only lose and not win. But for the system I was designing, I decided to have a win condition just be a part of every game. We might also want to allow multiple ways to win, but again for BlueCap we decided to just allow one win condition. Then you can see underneath here we've got a couple of events that apply after a player takes a turn. So these are fairly generic rules that can be mixed and matched together, and some games like noughts and crosses don't have any at all. So therefore we know we don't need to have these, so we'll allow our games to have anywhere between 0 and 2 of these after-turn events. So we end up with a simple spec for a game that looks a bit like this. So between this and our design language, we could move on right now and start building the system. But probably your language at this point, much like Blue Cap's, will be a little bit on the simple side because of the way we've started with inspiring set games only. And that means that the overall design space will probably be a bit small. So small design spaces can be really good, but if they're too small, they probably won't contain much to surprise us, and they might be a little bit too easy to search. The main way we're going to expand Blue Cap's design space is by extending its language with new components. Extending the design language might mean adding more options to an existing category, for example, a new win condition. It could also mean adding new categories altogether, which might require modifying the structure that we're going to design. For example, if we decide to add lose conditions, we'll need to modify the game structure we just defined so that it has a slot for a lose condition. However, this is the best time to do something like that. Once we start building the system itself and writing code for the games and ways to evaluate them, it gets a lot more painful to change the underlying structure of what you're going to generate. It's still feasible, and I do it all the time because we all forget stuff, but it just takes a bit more work. So it's good to have these thoughts now before we start building the system. Now, when adding to the design language, we might also want to pull concepts in from games we like, especially games that are similar to those in our inspiring set, but that we didn't actually consider at the beginning. So for example, we could add an after-turn rule that deletes rows that are completely filled, just like in Tetris. We can also remix existing logic to use it in other parts of the design language. So our reversey rule, which captures pieces that are bookended by pieces of the other player, could also be used as a win condition. So you win if you can bookend another player's piece, for example. Now in both of these cases, the adding the rule from Tetris or reusing the reversey rule in a different way, we don't know if either of these two things will lead to good game designs. But they feel like they are components that might be interesting to experiment with, and that's reason enough to include them in the design language. So when expanding our design language, it's useful to ask a few basic questions for each addition, so we get a feel for the kind of changes we're making to the space. So first, what exactly is it that we're adding? So sometimes this is very straightforward, so if we're adding a new win condition, then that's it. But sometimes we might be adding a set of possibilities rather than a single new possibility. For example, if we added a third dimension to the board size, which could also take a value of between 3 and 10 tiles, then we're not just adding one new board size, we're adding hundreds of new board configurations. So being clear about exactly how much we're adding to the design language is really important. The second is what excites you about this change. So it might be that you can imagine this change enabling a really good kind of game design, sort of like our inspiring set from earlier. But more often than not, it'll just be something that makes you interested. So the best kind of addition is one that makes you ask a question about the design space, or one that makes you curious about something. Is it possible to design a 2-player game that has Tetris's deleting filled rows rule? Additions that excite or interest you are always good ones to make. The third question is, how is the density of the design space changing? So by density, I mean the ratio of acceptable outputs to bad outputs. Of course, we can't know this exactly, that's why we're building the AGD system, so we have to act on feeling, but we really only need to judge it within an order of magnitude. Most additions to the design space barely alter the density. They add some good ideas and they add some bad ones, and if you have a hunch that you want to add it, they probably add enough good ones to balance it out. However, some changes will add a lot of noise, and these changes should be considered very carefully. For example, suppose we wanted to allow some tiles on the board to be marked as blocked from the beginning of the game, meaning that players can't play pieces on them. This could open up a lot of interesting new designs by allowing us to change the shape of the boards. But if any tile on the board could be blocked, this would massively increase the design space. For a 5x5 board, there would be over 33 million different board designs with different tiles being blocked off. If we want to add this kind of mechanical possibility without exploding the design space, we might want to think of more restricted ways to add it. For example, we could design a few templates of blocker tile patterns, like a checkerboard pattern or a ring pattern, and allow these to be chosen from a big design set, rather than allowing any arbitrary combination of tiles to be blocked off. This will limit the novelty and ingenuity of the block tile mechanic, but in return we get a much more tractable design space modification. Automated game design is design. It sounds obvious, but it's easy to forget when we're viewing it through the lens of AI research. There is no optimal video game, except perhaps Cooler World for the PS1. So before we even start, we know we're not trying to find the right way to design games, just a way, and hopefully a way that reveals new things to researchers, to designers, and to us. Hopefully, as you build out your design space and think about the questions you want to ask, you'll find yourself curious about different parts of it. Try making games using the design language yourself. Try thinking about questions you'd like to answer about the space that you've marked out. On paper, automated game design can seem antithetical to the art of game design. But in reality, I think that it's just another way to dive deeply into it and celebrate its depth and complexity. And hopefully you'll find a similar joy in this process too. Whatever algorithm or system structure you use, at some point you'll need to evaluate the work produced by your system. For most automated game designers, evaluation will be a big part of the design process, especially for search-based approaches, where the AI system needs a way of tracking its progress and ensuring it's making the right decisions as it works. Evaluation is always difficult for AI systems, but for AI that work in creative domains like video games, it becomes even harder. Games are evaluated by many different groups of people across many different metrics. A business executive, for example, illustrated here by Microsoft's Phil Spencer cosplaying my best friend's dad circa 2003, might be primarily interested in how many copies the game will sell or how marketable it is. A game designer might be interested in the tightness of the game's systems or how it feels to play. They might also have artistic aims they wanted to achieve with the work and whether they feel they succeeded. And beyond this, we have many more qualities that we often describe games as having. We call games challenging, moving, addictive, or simply fun. Not only are these qualities all very different and often in conflict, but you may notice that a lot of them are almost impossible to write down a formal definition for. Many of these words are intangible ideas that two people don't normally completely agree on. Just think of any time you've disagreed with a friend about whether a game is fun or whether a movie is good. Between people, this kind of disagreement can be fun and is part and parcel of how creative communities evolve and grow. But that doesn't help us when we want to give our AI system a clear definition of whether a game it's just designed is worth playing or not. One of the really important facts I want you to take away from today's talk is this: there is no way to objectively measure a game's goodness. That's why there are so many different game designers, that's why there's so many different games communities and schools of thought and game design trends and genres and generations. Making games is a subjective creative art form, and you cannot define your way out of this problem. But the good news is that this won't be a big problem for us. It just requires a shift in our perspective on evaluation. So what can we do instead? There are 3 useful approaches to evaluating games that I want to tell you about today. The first is static analysis, where we try and prove things about the game before playing it. The second is human evaluation, where we get people to do the evaluation for us. And the third is agent-based playouts, which BlueCap uses and which we'll talk about in some detail. Static analysis works by looking at the description of the game and trying to infer certain things about it just from this information. This has been used to evaluate and filter games going right back to METAGAME in 1992 that we talked about earlier. I find it particularly useful for throwing away games that repeatedly exhibit the same bad properties, and it's very good for precisely excluding or including certain things in your design space. For example, in BlueCap, it's possible to generate a game with the win condition get 4 in a row on a 3x3 game board. There's no way I can win this game, it's mathematically impossible, so we can write a little analysis rule that spots certain bad patterns like this and then excludes those games before they get any further in the design process. A more sophisticated static analysis system might be able to reason about rules more generally. So in the latest version of Angelina, I've built a static analysis system that tries to infer when a game is not winnable, which it does by looking for chains of rules that lead the game towards a conclusion. Human evaluation is as straightforward as it sounds. We get someone to play the game and give feedback to the AGD system. This can be as simple as a yes-no, or it could be more complex, allowing the evaluator to suggest changes, for example. There's also the question of how many evaluators we're going to have. If it's a personally guided system, or perhaps a co-creative system working with a human designer, then we might just have a single evaluator and value their feedback very highly. However, if the system is receiving feedback from surveys or large groups of people, we might be aggregating the opinion of dozens or hundreds of players. Human feedback is great because it allows us to capture a little bit of real human opinion about a game, and that's as useful to an AI as it is to real game designers who regularly playtest their games to assess their progress. The downsides are fairly obvious. It's very expensive and very time-consuming. This means it often needs to be paired up with other kinds of evaluation so that humans are only brought into the loop when the system is fairly confident about what it's showing. It's also obviously a fundamental part of co-creative systems where a human and an AI work together. For a nice example of this, look at something like Antonius Laupis's Sentient Sketchbook or Matthew Guzdiel's machine learning-driven co-creative game design tools. Evaluating games with AI agents involves building several bots that can play our games and then setting up play sessions where they play against each other, or on their own in the case of a single-player game, while we record data about the game. You can think of these kind of like experiments. We can tweak both the game and the bots so that a particular situation is engineered with an expected outcome that we want to test. For example, a bot that plans ahead and chooses its move intelligently should beat a bot that behaves randomly. So we can test this theory by making those two bots play against each other 100 times. If the intelligent bot loses a little, that's maybe okay, but if it loses a lot, we might think that there's something wrong with our game design. One of the main drawbacks of this approach is that it relies on our ability to design bots that can play our games. We'll get onto that in a second. That means that if you're designing a game about writing and performing poetry, for example, testing it with bots will be pretty hard because designing bots to play that kind of game in the first place is a very hard task. Another major drawback is that bots don't always play like humans. For example, a bot can't get confused or intimidated, it can't misunderstand the rules or get tired, drunk, or distracted. So sometimes our tests might tell us one thing where human players would find the exact opposite. Learning to write the right kind of test just takes a little time and a little practice. Writing AI agents that can play games designed by an AGD system can be difficult because we won't know much about the game in advance, and so we can't give the AI extra heuristics or tips to make it play the game better. This makes the task similar to general game playing, another area of game AI where researchers try to build agents that can play any game even if they haven't seen it before. In BlueCap, we have 3 different kinds of AI agent that we use in our evaluation. We have a random agent, which on its turn picks a random empty tile and plays a piece on it. We have a greedy agent, which can look exactly one step ahead into the future, so it can see the direct consequences of an action, and then it simply picks the action with the best reward. So the greedy agent is slightly better than the random agent because it will avoid making a move that causes it to lose and will always take a move that causes it to win. However, it can't plan ahead for the long term. Finally, we have an MCTS agent. MCTS, or Monte Carlo Tree Search, is a very useful algorithm that is good at playing games without any assistance, using simulations and random playouts to methodically decide what the next best action is. The MCTS agent can be tweaked to give it more or less computational resources, so we can use it to simulate stronger and weaker agents as well, which is really useful. So we can mix and match these agents to test different theories about a game that we want to be evaluated. In our evaluation process, which you can find in the game evaluation CS file, our system steps through 4 different game matchups from which it measures 5 different qualities. I'll very briefly run through them here to give you an idea of our approach. So our first evaluation is 2 random agents against each other. This is very fast to run because there's not much computation going on at all. This is to test one specific theory, and that's that the game isn't fundamentally biased towards one particular player. So we expect our random agents, since they aren't playing strategically, to win and lose roughly an equal amount of times, and probably not to actually win the game much at all. Note that this doesn't mean that the game is unbiased just because we pass this test. So, for instance, noughts and crosses is very biased in favor of the first player, but it requires a lot of planning and understanding to take advantage of this. So this kind of random versus random matchup is the lowest possible bar for our game to cross. Our next test is greedy versus random. So here we expect the greedy player to win more than the random player, but we don't necessarily expect much beyond that. So, for example, a complex game may require planning to reach victory, which the greedy player won't be capable of. But even in this case, the greedy player should be able to stay even with the random player because it will always avoid losing moves if it can. If the random player, who can't tell a losing move from a winning move, beats the greedy player, then that's probably a bad sign for our game. Our third test is another asymmetric matchup, this time Monte Carlo Tree Search versus the greedy agent. So as with the previous matchup, we expect MCTS to win again, but this metric is a little bit more important than the greedy random matchup. There are 2 reasons for this. The first is that the expected skill gap between the 2 agents is much more pronounced here, so we expect a similar big difference in outcome. And the other reason is our expectations about the game itself. So since we want to design games which require strategy and planning, we expect that an agent that can plan into the future should be able to perform better at a game if it supports that kind of planning. So this is really explicitly testing a design theory about our space. Now our 4th and 5th tests are both measured from the same matchup, which is 2 MCTS agents of equal strength playing against each other. So this is our highest skill matchup, so we expect this to give the best imitation of 2 good human players who are trying to win. Given that both of our agents have the same strength in terms of the amount of time and computational resources given to them, we can use this matchup to measure two things. First, the number of games that end in draws. So we probably want our game to be decisive. We don't want games to end in draws too often, so we prefer games that have fewer drawn outcomes in this high-skill matchup. The second expectation here is that neither agent should have a particular advantage. So this is actually mirroring the random versus random test, but at a higher skill level, and so testing kind of a different angle of the first player bias factor. To see our test in action, you can open and run the generate scene, press play, and watch as the game generator generates 100 games and evaluates each one in turn. So there's no intelligence or complex algorithm here. It's literally just showing you what is the best game that came out of testing 100 random games. When designing tests like this, it's worth bearing in mind that, like any data gathering exercise, the more data we have, the better our conclusions are. That means that running 20 matchups is better than running 10, and so on. However, this can be costly if you were using a search-based approach like computational evolution, where thousands of games might need to be evaluated in a single design run. The same goes for the resources given to a single agent. So stronger MCTS agents with more time and computation given to them will give us much better data on our game. But this will mean that we spend a lot more time evaluating games because it takes a lot longer to think up how to take a single move. Before we close out the evaluation section, I wanted to tell you quickly about two other systems that incorporate slightly different evaluation approaches. The first is Variations Forever by Adam Smith and others, which uses answer set programming to define constraints on a design space. So in this approach, a designer or a player alters the constraints, which results in different games coming out of the answer set system. So this is similar to human evaluation, but because the constraints are always met, we can think of it more as a process of refinement by the human user, rather than just subjective feedback. If you're building an AGD system with a machine learning component, we can also think of its evaluation process as being slightly different too. So machine learning systems often use human evaluation to provide feedback to a live system. Matthew Guzdial's co-creative designer is a good example here. But we can also think of the act of learning as internalizing an evaluation of sorts. If we train a system on examples of good and bad design content, then the learned model in some ways is an internal sense of evaluation that the system has developed. So we're delving a little into semantics here, but I wanted to point out this example because evaluation comes in many forms. Evaluation is a very hard part of building an AGD system, but it can also be the most fun because playing broken or suboptimal games is very rewarding, and it helps you think about game design and about the design of your AGD system. As you get games coming out of your AGD system, you'll get a chance to re-examine the ideas that you encoded in the first place and get opportunities to go back to tweak and improve things. You'll see that BlueCap's very simple evaluation leads to a lot of weird games. Its main weakness is that the default settings don't run very deep evaluations because I wanted it to be able to completely generate a game in a relatively short space of time so that you could play with it. If you want to experiment with better results, try turning some of the settings up a bit, using more runs for each evaluation, giving more resources to the MCTS agents, and then leaving the system to design for a few hours. Even then, you'll still find games that are interesting at first, but kind of turn out to be broken, often in unusual and subtle ways. Even though these games are not going to be award winners, I still find these kinds of examples the most exciting to get from an AGD system, and finding out exactly why they're broken and how this slipped past my evaluation system is always a really enjoyable puzzle. Before we close out this practical section, I wanted to touch on the issue of actually building one of these systems. So a lot of the theory we've discussed so far works great on paper, but making games is really hard, and a lot of unusual software engineering challenges can come up when building a game-making system. The first question is, what game engine should you use? If you're building an AGD system for physical games like card games or board games, you don't really need to worry about this. But if you're making an AGD system for video games, I really recommend building on top of an existing engine, saving yourself time and worry. Ultimately, the best advice I can give you for building better AGD systems is to make games yourself. Whenever I wanted to use a new engine for Angelina, I would first build some games in that new engine. Now this obviously takes time, and I know time is something we always need more of. And I also know that learning a new skill is painful. It can be very demoralizing at first, but finding a small community of a similar experience level to you is a great way to start out, and it will give you the confidence to learn and experiment. The best place to find this today, in my opinion, is on itch.io. Go there, join a game jam, set aside a weekend to enter it, limit yourself to just a few hours a day. You don't need to burn out doing 12-hour game jam days, and just make something really, really small. There are many great tools and game engines I can recommend, some of which are listed here. I've included links to each one of these in the description of this video. I want to particularly point out Haxflixel here. I worked in Flixel for many years, and it was a very satisfying game engine for making 2D games, especially action games. The logic of its game engine isn't too hard to get into, and it has a lot of useful helper code for doing common things. Also, don't feel forced to rush into using a popular or fancy technology. Try out tools, find something you enjoy, and learn to think small. Following other indie developers on Twitter and playing their games is a really good way to practice this. Without doubt, the hardest skill to practice as a game developer, and this is still true for me 8 years on, is learning to think smaller. The idea you have is always too big, and that goes for AGD systems as well as game development. So with that said, and with that big list of interesting game engines to experiment and try, my overall recommendation for a game engine, something to aim for as you get more confident, or perhaps you're already a developer and you just want the bottom line, you should use Unity. Unity is one of the most popular game engines in the world. Your university may well already teach it to their students, and it has a lot of nice advantages for us as researchers to supercharge our research work. In terms of quick positives, some of the big ones, it runs on almost any platform, which means you can easily export to mobile devices, to the web, even to modern games consoles if you have dev kits for them. And that means it's easy to run surveys and tests wherever you want, easy to share your work and make it portable. And that's one of the most rewarding parts of research. Because it's popular, you'll also find that most of the common problems you have already been asked and answered on places like Stack Overflow, and Unity has an asset store that is packed full of really useful and often completely free or very cheap utilities and assets, and that can help out with everything from animation to user interface to AI. And it uses C#, which is a pretty nice, clean language with good support and lots of features. Now, Unity isn't without its downsides, the most important one being that it's quite a big tool, and if you're new to making games, it might be a bit daunting. And for some projects, it's probably overkill. However, learning Unity has lots of useful side effects, especially if you work with students who might be learning it too, or using it on other projects, or if you want to build general tools that are used by, for example, other game developers. The other major downside is that Unity requires a little bit more planning in order to export your games, which is something we're going to talk about in a bit. If you are interested in learning Unity, I'm always happy to chat and give feedback and help. And I've also added a link to Tom Francis's excellent YouTube tutorial on making a game with Unity, which I highly recommend. So once you've picked out your game engine, you're ready to start building your system. There's a few hurdles that often catch me out at this stage, and they may or may not apply to you depending on what kind of system you're building, as well as what tools you're using and what kind of games you want to make. So the first thing I normally do, regardless of what system I'm building, is I make a template game that sets up all of the basics that every game generated by my system will have. So for BlueCap, that means a game that creates a board of tiles of a custom size, allows me to tap a tile to place a piece, swaps between players after each turn, that kind of thing. So then on top of this, we add any features in our design language. So not that they should all be active at the same time, but so that we can easily turn them on or off. So there's a few ways that you can do this. In BlueCap, you'll see that the way I do it is to create classes that represent different parts of the design language. So there's a condition class, which is sort of an abstract class that is subclassed for the inner row condition and the total piece count condition. And then games can have condition objects that they use to check the game logic for winning and losing. Now, there are more flexible routes you can take to this, and a lot of it will depend on the language you're writing code in and how confident you feel. For example, C# has delegates, which is a feature that allows you to wrap a method call and use it as an object, so you can move it around and invoke it wherever you want. I really like this feature, and there's a lot of similar features in other programming languages, and they're really useful for chopping and moving around game code at runtime. The other key piece of the AGD engineering puzzle is figuring out how you want to distribute and export your games. So whatever algorithms and techniques you use to solve the automated game design part, at some point your system has to output something. So in terms of output, the two best approaches I've come across are game description files and directly modifying a template game's codebase. So in the former case, we just write out a simple text file, usually in a machine-readable format like JSON, that describes the structure of the design produced by the system. So if you're making a level designer, for instance, this game description file might include the locations of all of the world geometry and any models used. If you are developing rule sets, it might be a description of the win conditions and the rules applied at different stages of the game. So this approach is nice because it produces very small and compact outputs, so your system is just producing a tiny text file, and we can write a parser to actually load these descriptions back into our system, which opens up lots of exciting opportunities, like allowing us to read game designs made by people, not just by our system, or reading back in old designs that we worked on in the past and then continuing to work on them in the future. The other approach I've used is modifying the code base of a game directly. So when I was working with Flash games, I had a full template game with gaps in the code at key locations, such as the update loop, marked with specific tags. And then when the AGD system was ready to export a game design, it would generate and then paste code segments into these tagged areas, and then use the Flash compiler to compile the template game. This loses some of the advantages that a smaller, simpler text file output has, but it's also more flexible and it doesn't require us writing a whole interpreter to parse game descriptions. The final step of the process is deciding exactly how you want to distribute your games. So if you're generating simple game description files, then you can distribute a standalone interpreter, which means that players simply need to download new text files and load them into this interpreter that they already have on their machine. Or you could allow the interpreter to contact a server that you have and then download the latest game descriptions that you've uploaded there. This requires more engineering both at the beginning of the project in order to build the infrastructure for the interpreter, and as the project continues to make sure that the interpreter is up to date with all of the changes to your design language and also backwards compatible with the old versions of games that you've already published. However, the benefits are that your system is much more flexible, and distributing your games is also somewhat simpler, especially if you intend to automate this process. For example, you can't automate the process of uploading projects to Steam, but you could upload a single interpreter to Steam and then automate the process of uploading text files to a server that you own. The other approach is the baked approach, where you export a standalone game that doesn't need anything else to play. So if you take the template game approach that we just mentioned, and then you compile the modified template, you end up with a standalone game that can be uploaded and distributed however you like. So why would you want to do this? Well, for one thing, it's a lot easier to do it this way. But a bigger reason, in my opinion, is exhibited by this image here, which is the top of Angelina's itch.io page listing all of its games. On the left, you can see the interpreter for Angelina's latest game engine, which allows you to load up new game descriptions and play its games. On the right are standalone games made by the last version of Angelina that you can start playing with a single click. So which one of these are you more likely to play? Convenience, nice looks, simple descriptions, they're all important factors in getting people to actually play the game that your system makes. As developers of AGD systems, just like game developers in the real world, we have to be marketing experts as well as designers, engineers, and everything else. This is another small but significant trade-off to consider. Speaking of itch.io, before we close out this section, what should you do with all of these games your system has made? My recommendation is that you get familiar with the amazing website that I've already mentioned a couple of times in this tutorial, which is itch.io. This is a huge storefront that doubles as a community space for many, many creators, and also has a thriving jam scene where dozens of game jams are often going on at any one time. Signing up to itch.io gives you a unique URL where you can upload games as well as other projects and organize them neatly with custom designed pages, screenshots, trailers, and lots of other stuff. You also get access to really good analytics pages showing what games are being played and downloaded, where people are coming to your page from, and so forth, which is really useful if, one of your games gets shared somewhere famous and that you don't hear about until it's too late. It's a fantastic website made by really, really good and dedicated people, and you can use all of its amazing features completely for free. So if you only do one thing as a result of watching this tutorial, please go and register an itch.io account and get involved in the community there. It's one of the best ways to experience the work of modern game developers of all scales and styles, and it's a great way to share your own work too. I also recommend making YouTube playthroughs of the games that you distribute from your system. This is really useful for a couple of reasons. First, lots of the people interested in your work may not play or enjoy video games, and so being able to watch someone play the game and see how it works is really valuable, and it can help people like journalists or other researchers understand your work better and in less time. Second, it's a sad fact that video games are not a very durable medium, especially if your games are not super famous. When making various AGD systems, I tried to choose technology that I thought would last the longest, but even some of those platforms are now beginning to crumble like Flash. So recording videos of our games is important because 10, 20, or 50 years from now, they may be the only way to experience these games. And while our games might look silly and not amazing, life-changing works of art, they are all really important parts of the history of the field and of games. Even making a talk like this, barely 10 years into the prime of the field, it's hard to find records of some of these systems. It's really important that we do our best to preserve the research we do, and recording video is a good way to do that. I've tried to pack as much advice as I could into this central practical section of the tutorial. Before we move on to closing out the tutorial, I just wanted to emphasize that this field is very, very new in the grand scheme of things. Only a handful of systems exist, and while we can see some patterns in how successful systems were built, there's so much room for experimentation, for new ideas, and for better ways to be discovered. So don't be afraid to get out there and build things the way you want to build them. That's what most of us are doing, and learning about what works and what doesn't is part of the joy of research. You can download BlueCap on my GitHub. It should open in the latest version of Unity and work right out of the box. There's a lot of comments in the code and some scenes that let you run examples right then and there. And there's a few other things that I'd like to add to it, like an example evolutionary process, which I will try and do in the coming months, but I don't need to tell you what academic promises are like. So we've talked about what automated game design is, we've looked at the history of the field, we've discussed why you might want to do it, and now we've also looked at some practical issues that come up when we actually try and build one of these systems. Before I close out this tutorial, I want to talk to you about some ideas that really matter to me about the future of this field and the kind of directions that I think we should be taking our systems in. When we talk about automating processes with AI, we often focus on the automation of a task. For example, automating the analysis of brain scans to detect illness is automating a specific task. Sometimes when we build automated game design systems, we're also doing this. If we build a system to measure the distribution of puzzle difficulty in a level generator and advise a designer on an optimal fix, we're probably focused just on performing that task and that task alone. However, the bigger questions in this field come not from the simulation of a task, but the simulation of the person performing the task. I would argue that when we build an automated game designer, our real intent is not to simply automate the production of games, but to build a system capable of taking on the same role in society that game designers have. Our systems cannot create in a vacuum, whether they are teachers or assistants, colleagues or critics, leaders or followers. Our AGD systems are ultimately destined to exist in a social context with other creators and audiences, and we should never lose sight of what this means. Mihai Csikszentmihalyi, best known for his theory of flow, wrote a paper in 1999 where he modeled creativity as a system. The model represents the creative individual and how they're affected by and contribute to the community and the domain that they're creative in. I really like this work because of how explicit it is about the importance of the context around creative systems. But what really sold me on the model was when I heard Rob Saunders talk about it and his own modeling of social cliques. Rob presented a great talk in 2013 at an autumn school in Finland, a recording of which is still online, and I've linked it in the description of the video. Rob talked about Csikszentmihalyi's models of creativity, as well as Rob's own models of creative communities, or cliques, where individuals had their own ideas and knowledge and influenced others in the community by being creative. Each little creative agent would have a chance of learning something by looking at the work others created, and this would influence their own work in turn. Some agents might move between communities or cliques as well, meaning they took ideas from one space and introduced them to another. Rob spoke really passionately about the idea that we can't simply think about AI as creative individuals, but instead we have to think about how they exist in a wider world. Since 2018, I've been thinking about how we can build creative systems that live up to Rob's model of an individual in a creative community. How can we build AI systems that don't just spew out artifacts, but that exist in a community of people and other AI systems and that meaningfully contribute towards it? If you're interested in hearing me talk more about this, I gave a talk at the International Conference on Computational Creativity about these ideas, which I've linked in the description of this video. But the gist is that in order to achieve this, I believe that we have to build systems that have a creative process of their own, where creating a finished work is just one small part of what they do. Just like people, these creative AI systems need time to rest, time to learn, time to experiment, and time to reflect. Building AI systems that do all of these things not only results in better systems, but also gives the community around that system more opportunities to engage with it, learn about it, and become invested in it. My work in this area will hopefully be restarting once I move back to the UK later this year, and I hope you'll follow Angelina's progress and support the system as it starts making games again. But why would we want our AI systems to join and organize creative communities rather than just producing things? Creative communities exist everywhere. Your household, your family, your friends, and your text groups are all creative communities. In the age of the internet, however, the biggest creative communities we are a part of are online, usually on social media sites like Instagram, Twitter, YouTube, and TikTok. These sites are made up of millions of smaller fluid communities like the people you follow on Twitter or the subscribers to a particular channel on YouTube. But they also form a larger creative community as the sum of their parts. But perhaps the most important feature of these communities is that they're only partly mediated by people. The most important influencers on these sites are algorithms designed and implemented by the platform holders whose primary interest is in profiting from the site. This leads to a number of bad outcomes, each of which could sustain an hour and a half's worth of discussion on their own. Although in theory these algorithms work to support users and creators, in reality algorithms eventually become the driving force behind the sites. Creators make content that they think the algorithm will respond favorably to, and audiences are led to whatever content the algorithm is optimizing for, which is more likely to be based on engagement metrics like minutes watched, rather than true enjoyment or interest. And all of this adds up to a very unsatisfying whole. Are we all able to reap the benefits of these creative platforms equally? Can we all find spaces to grow and experiment within? Or are we being lumped together by algorithms to be fed content from a small fraction of the most profitable creators? The musician David Byrne wrote about how systems like this tend to shape our thinking about creativity and encourage us to consume rather than enjoying the act of creation. The act of making music, clothes, art, or even food has a very different and possibly more beneficial effect on us than simply consuming those things. The way we are taught about music and the way it's socially and economically positioned affect whether it's integrated or not into our lives, and even what kind of music might come into existence in the future. Capitalism tends towards the creation of passive consumers, and in many ways this tendency is counterproductive. Now, I realize you probably didn't tune into this tutorial for a lecture on the ethics of techno-capitalism. And that's fair enough. But I think about these ideas more and more often recently, and I think about how AI research is often complicit in constraining and constricting these creative spaces and enabling those who profit off doing that. If we want to build AI that truly enriches people's lives, I don't believe we can look to centralized solutions where a massive system is controlled by a single organization that everyone else is dependent on. I think we need to focus on building systems that are fully owned and operated by small communities, and that don't require huge computational resources to create or maintain. We can help to do this by building creative systems that embody the creative individual, not just the creative act. These systems can help take on the labor of building, maintaining, and growing creative communities, and become active participants which teach and are taught, which lead and are led, which create and also play. This is the future that I want to build with AI. We're really close to the end of this tutorial now, but before I wrap up with some conclusions, I wanted to leave you with some ideas of where this field might go next, and a few open problems that you might like to tackle with some AGD systems of your own. As I've mentioned throughout this video, one of the problems with automated game design that we've also seen in procedural generation research is a focus on a very narrow and recurring set of design spaces. Arcade games, platformers, puzzle games, that sort of thing. A great starting point for people interested in making an impact in automated game design is to look at design challenges in genres that are much less explored. So dating sims, slapstick physics games, and crafting games are a few examples that spring to mind. These will be challenging new spaces to explore, but are full of new design problems to think about and approach. Alternatively, trying to build systems that work on what I call Goliath problems are also rare. Most automated game design systems focus on small game experiences like puzzle games with a few levels, or a self-contained platforming experience, or a very simple strategy game. This makes sense on paper because smaller design spaces are more tractable, and thus it's more likely that we can build systems which perform well working within them. However, there's a lot of value in trying to take on tasks which, right from the outset, we know are already implausibly massive. The National Novel Generating Month is a good example of this, in which entrants attempt to generate a 50,000-word novel in the month of November. And this is in contrast to most story generation research, which works on a smaller scale. Although this task is much harder to do competently, the additional challenge forces people to innovate, develop different techniques, and find solutions to problems which simply don't arise when working at smaller scales. So with that in mind, why not try writing an automated game designer for 50-hour JRPGs or massively multiplayer online games? Try generating open-world action games or vast prestige dramas. You will almost certainly end up making a system that is messy and broken, but equally I can guarantee you that you'll uncover problems, and hopefully solutions, that the rest of us have never even thought of before. Finally, I want to recommend approaching wicked genres. I'm borrowing the term wicked here from Alex Jaffe's 2019 GDC talk on cursed game design problems, which in turn is a reference to wicked problems, a term coined by design theorist Hurst Rittel. Jaffe describes cursed game design problems as problems without a solution, but I'm not thinking quite that drastically here. Instead, I'm leaning a bit more on Rittel's original definition. Rittel defined wicked problems as a special class of super problem, like climate change, world hunger, or nuclear disarmament. These problems share a few properties that I'm borrowing here. People don't quite agree on the definition of the problem. It's really hard to evaluate and agree on how good a solution to the problem is. And solutions aren't correct or incorrect. Instead, they're on some kind of nebulous spectrum of goodness. Wicked genres for automated game design are genres where even the most fundamental design questions are wrapped up in subjectivity and human faculties. Walking simulators like Firewatch are a good example of a wicked genre. Their design relies heavily on narrative design, on environment design, lighting, vision, sound. Almost every aspect of the genre is itself a huge challenge to overcome. I began and abandoned a couple of automated game design systems targeting this genre, and although I've not given up on it yet, and you shouldn't either, it's definitely a tough one. We need fresh perspectives about how automated game design can be done, and this will open up new ways to build AI systems that can help shed light on even the most wicked of genres. I really hope more people are tempted to jump right into a problem like this. Thank you so much for watching this tutorial and for listening to me talk about a subject so close to my heart. Before I leave you to enjoy the rest of COG, I wanted to leave you with some closing thoughts and then some links where you can find out more about my work and about automated game design in general. As we saw throughout this talk, automated game design is a wild frontier of AI research to which anyone can bring a new perspective. Novel AI techniques combine with individual views about game design and development and result in AI systems that not only create fun and inspiring games, but also help us gain a different perspective on how games function, what they can be, and how we should make them. Automated game design can be framed like a lot of other AI research, a quest to obtain more for less. More profit, more content, more control, for less money, less risk, and less people. But it can also be framed as a way to give people the support they need to build creative communities around them, in a time when creativity is increasingly controlled, commoditized, and curated by algorithms. It can also be framed as an artistic pursuit, a way to study and understand games better by modeling our own thought processes about them. And it can be a way to appreciate and celebrate an important part of our humanity by stepping outside of it to consider it from another perspective. I hope this talk has provided some insights for you and you feel encouraged to start work or continue working in this area. Whether you're excited by something I showed you today or simply motivated to prove me wrong about something, I want as many people to join this field as possible and to keep expanding our idea of what AI is for, what game design is, and what games can be. Thank you all again so much for watching. If you enjoy hearing me talk for way too long about things that are way too specific, you might enjoy my YouTube channel, my blog, or the h.io page where I post my games. The links to all of these things are in the video description. If you want to ask questions about any topic that's come up in this talk, or about related topics in game design or AI research, I'm always happy to chat. You can get in touch with me on Twitter @mtrc, or you can drop me an email, mike@possibilityspace.org. And in a few months' time, I'm hoping to make a short Q&A video where I answer any frequently asked questions or respond to comments that have come up since then. So feel free to leave a comment below or get in touch with me via any of those other means. Thank you all again for watching. I hope you enjoyed it. I hope you enjoy making things that make things. And I also hope to see you all again in the real world real soon. Bye.